Okay, so good morning, everyone. So, hello. So, we are the ninth presenter for today, Block Jack, and we are going to specifically talk about vertical curves, which is the second part of seventh unit in our syllabus for CE 101 or surveying. So, if you can recall, the last topic tackled was horizontal curves, which was the first part of Unit 7 and was tackled by the 8th presenter from our block. But today we're going to talk about vertical curves specifically, which are, of course, different from horizontal curves. So, the presenters that will give the information to you and will explain all the concepts, formulas, derivations, and solving portions of this topic are class number 7, Wayne Ko, class number 25, Renoir Monleon, class number 31, Najel Sarvida, and class number 40, Jonathan Yu. So I hope you sit back, relax, and hopefully this will be super useful in our course and enjoy the report. Okay, so first and foremost, before we tackle about the vertical curve, let us differentiate it from the horizontal curve. So what is the difference of the horizontal curve and the vertical curve? So I think by now we have an idea on what the horizontal curve is since it was reported by the previous group. And I think we have an idea now on how it works, how to solve it, and stuff. And now as we are approaching on the latter part of Unit 7 in our modules, we are going to talk about the vertical curve. So this is the last topic na jud sa Unit 7. So to differentiate it, like what Group 8 discussed, a horizontal curve is mostly a curve that changes the alignment or direction of the road. So you can see that as an example in the first pic, kaning top left. So that is an example of a horizontal curve. Meanwhile, let's take a look at the bottom right pic. That is an example of a vertical curve. So these are curves that change the slope of the road. So let's apply it in like real life situations para masabtan jud natong concepts nila. So let's just say we are driving, okay? Like I think, or let's just say nagsakay tag jeep. Okay. So when the car or the jeep or like any vehicle that turns left or right due to the direction of the road, so the horizontal curve plays a role in that. So these are the curves that make our car turn right or left since we have to follow that direction for safety purposes. So that is an example of horizontal curve. Okay, so if ang horizontal curve kay left or right siya, like in our perspective as we are riding a vehicle, sa vertical curve, it is more likely up and down. Kay we are dealing with the change of the slope of the road. So of course, let's just say nagsakay to car karon, then the jeep or like the car like passes through a very steep hill, then yeah, that is an example of a vertical curve. So the vertical curve plays a role in that. So kuha na. So remember lang dyan na, if we are riding a vehicle, if the direction of the road from like left to right, that's a horizontal curve. From up to down, manang vertical curve. I think that's all you need to know for the differences. And I hopefully this can be useful as we are going ahead with this lesson. Take note.
What are vertical curves? Vertical curves are the second of the two important transition elements in geometric design for highways, the first being horizontal curves. A vertical curve provides a transition between two slope roadway, allowing a vehicle to negotiate a elevation rate change at a gradual rate rather than a sharp cut. Because these curves exist in vertical plane, they are called vertical curves. The design of the curve is dependent on the intended design speed of the roadway, as well as other factors including drainage, slope, acceptable rate of change, and friction. These curves are parabolic and are assigned stationing based on horizontal axis. So what does vertical curves do? Vertical curves are used in highways and street vertical alignment to provide a gradual change between two adjacent grade lines. Some highways and municipal agencies introduce vertical curves at every change in grade line slope, whereas other agencies introduce vertical curves into alignment only when the net change in slope direction exceeds the specific value. Here are some factors to be taken account in designing a vertical curve. Providing a good fit with the existing ground profile, thereby minimizing the depths of cuts and fills. Balancing the volume of cut materials against fills, maintaining adequate drainage, not exceeding maximum specified grades, and meeting fixed elevation such as intersections and other roads. Paying more attention to the drainage design when value is k is greater than 167. The length of vertical curve can be computed by using k values in both crest and sag vertical curves. Minimum length of the crest vertical curve is equal to 3 times the design speed only on English units. The roller coaster or the hidden up type of profile should be avoided. Two vertical curves in the same direction separated by short section of tangent grade should be avoided. On long grades, the steepest grade should be placed at the bottom of the curve and flatten the grade near the top of the ascent. It is desirable to reduce the grade through the intersection where at grade intersections occur on roadway section with moderate to steep grades. Sag vertical curves should be avoided in cuts unless adequate drainage can be provided. The stopping sight distance of truck is not necessary to be considered in designing vertical curves because the truck driver is able to see further than passenger car. For that reason, the stopping sight distance of trucks and passenger cars is balanced. In most cases, the stopping sight distance will be used for vertical design length, but engineering judgment also get involved in decision making. Drainage of curved roadways need to retain a grade of at least 0.5% or sometimes 0.3% for the outer edge of the roadway. For appearance, the minimum curve length can be calculated by equal to L is equal to 100A for small or intermediate values of A. For the important conditions for the curve design, fit the grade lines they connect have lengths sufficient to meet specifications covering a maximum rate of change of grade, which affects the comfort of vehicle occupants, and provide sufficient sight distance for safe vehicle operations. There are two types of vertical curves, sag vertical curves and crest vertical curves. Sag vertical curves are curves that connect descending grades, forming a bowl or a sag. Designing them is very similar to the designs of the crest vertical curves. Once again, the sight distance in the perimeter that is normally employed to find the length of the curve, while crest vertical curves are curves that connect inclined sections of roadways, forming a crest, and they are relatively easy to design. The principal control in design of the crest vertical curves is to ensure that minimum stopping sight distance, or SSD, is available throughout the vertical curve. An appropriate length of the curve is required that will accommodate the correct sight distance. The sag vertical curve has two formula. If the sight distance is found to be less than the curve length, the first formula sight distance is less than the curve length is used, wherein L is equals to AS squared over 200 times H plus S tangent beta. The second formula is used when the sight distance that are greater than the curve length, wherein L is equals to 2S minus 200 times H plus S tangent beta over A, wherein A is the absolute difference between G2 and G1 multiplied by 100 to translate to percentage. S is the sight distance, H is the height of the headlight, and beta is the inclined angle of headlight beam in degrees. The crest vertical curve have also two formulas. The correct equation is dependent on the design speed. If the sight distance is found to be less than a curve length, the first formula is used, wherein L is equals to AS squared over 200 times the square root of H1 plus square root of H2 squared. And the second formula is used for sight distance that are greater than the curve length, wherein L is equals to 2S minus 200 times square root of H1 plus square root of H2 squared over A, wherein LM is the minimum curve length, A is the absolute difference between G2 and G1 multiplied by 100 to translate to the percentage, and distance site is S. H1 is the height of the driver's eye above roadway surface, and H2 is the height of the object above roadway surface. So what is stopping sight distance? We mentioned stopping sight distance or SSD in the factors. So stopping sight distance is the near worst case distance a vehicle driver needs to be able to see in order to have a room to stop from colliding with something in the roadway, such as pedestrians in a crosswalk, a stopped vehicle, or a road debris. Sight distance is dependent on the type of curve used and the sight speed. For CREST curves, the sight distance is limited by the curve itself, as the curve is the obstruction. For SAG curves, sight distance is generally one or only limited by headlight range. ASHTO has several tables for SAG and CREST curves that recommend rates of curvature, or K, given a distance speed or stopping sight distance. This rate of curvature can then be multiplied by the absolute slope change percentage, which is A, to find the recommended curve length, LM. So AASHTO means American Association of State Highway and Transportation Officials. Without this table from AASHTO, curve length can be calculated. Formulas have been derived to determine the minimum curve length for required sight distance for an equal tangent curve, depending on whether the curve is sag or a crest. Since vertical curves is parabolic, we will be using the general equation of the parabola, which is y is equal to ax squared plus bx plus c, turning it to y sub p is equals to ax squared sub p plus bx sub p plus c in relation to the parabola. Parabolic functions have been found suitable for this case because they provide a constant rate of change of slope and imply equal curve tangents.
Okay, so now we move on to the elements of the vertical curve. So of course, these are the elements or variables involved in a symmetrical vertical curve. So take note, this applies for symmetrical curves. Asymmetrical curves have different concepts, but of course, they are closely related and they are closely similar to here. So without further ado, all of these variables that you see in the picture in the right, of course, they play a role and they have a function in the vertical curve. So of course, it's important to learn the elements for first before delving to the formulas, derivations, and solutions. So let's first tackle about each and every one of these elements. Let's go. So let's start off with the first element that we can see here on the diagram on our right side. I encircled it so it can be clear. So the what is encircled there is PC, and PC stands for the point of curvature. So the point of curvature, it is also coined as the beginning of the vertical curve, or BVC. We can see that from the name itself, it is actually what starts the vertical curve. And the point of curvature is actually the intersection of the curve right here, the vertical curve, and the back tangent. So the intersection of the back tangent and the vertical curve is the point of curvature. And I just want you to remember that the point of curvature is what starts the vertical curve. That's what all you need to remember. So now we move on to the point of tangency, and it is quite just the opposite of the point of curvature. So if the point of curvature begins the vertical curve, the point of tangency ends the vertical curve. As you can see here, it is also coined as the end of the vertical curve, or EVC. And notice how the point of curvature is forming a back tangent, while the point of tangency forms a forward tangent. And it is actually the name itself. The point of tangency is literally the point of tangency between the vertical curve and the forward tangent. So to rephrase that, the point of tangency is the intersection of the forward tangent and the vertical curve. So I think Basically, the summary here is just the point of tangency ends the vertical curve, and the point of curvature marks the start of the vertical curve. And then we also have the point of intersection of the tangents. So we call this the point of vertical intersection, or actually, as what is labeled on the diagram, it is just PI. So if you can notice the leftmost portion of the diagram, what is encircled there is PC. It starts the vertical curve and it starts the back tangent. It forms the back tangent. And if you look at the rightmost portion of the diagram on what is labeled as PT, or the point of tangency, it is the intersection of the vertical curve and the forward tangent. So it forms the forward tangent. So basically, the point where the back tangent and the forward tangent intersects is basically the PI, or the point of intersection. So that is pretty much all you need to know from the first three elements of the vertical curve. The point of curvature starts the vertical curve, the point of tangency ends the vertical curve, and that the tangents that the point of curvature and point of tangency form has an intersection, and what the point of intersection is called or coined is the PI, or the point of intersection. So that's basically it. So now we move on to L. As we can see on the diagram on the right side, on the lowermost portion, I encircled that L, and it stands for the length of parabolic curve. So it is actually just the projection of the curve onto a horizontal surface, which corresponds to the planned distance. So as you can see, it is basically just the horizontal length of the whole vertical curve. And yeah, it corresponds to the planned distance as well. So alongside L, the length of the parabolic curve, we also have A, and A stands for the change in grade from PC to PT. So notice in the topmost portion of the diagram, I labeled that A, which stands for G2 minus G1 if you look at the lower portion of the diagram. So basically, since it is the change in grade from the point of curvature to the point of tangency, basically the back tangent and the forward tangent with the grade limits, basically you get the area. And basically the area will stand for A and it will correspond to A. So we'll actually learn more about that later in the formulas and its derivation as we will discuss it. So yeah. So next up we have S1, which is the horizontal distance from PC, or the point of curvature, to the highest or lowest point of the summit, or the sag curve. So you can see that on the diagram on the left here, on the summit, you can see the horizontal distance from PC and the point of the summit. That is basically it. Whereas the S2, or the horizontal distance from point of tangency to the highest or lowest point of the summit and sag curve, it is just quite on the opposite side of the spectrum of S1. So they are just basically the same. It's just that S1 is they both they both have the same common point, which is the highest point of the summit. But the difference is just S1, as you can see on the diagram on the left portion, S1 starts from the point of curvature, while S2 starts from the point of tangency, as you can see on the right side of the screen. So we are almost done. We are only left with a few more variables. So let's continue. We have H1. And as you can see in this diagram, encircled in the left portion of the diagram, H1 stands for the vertical distance between the point of curvature and the highest point of the summit, or the lowest point of the sag curve. So that's basically it. Next, we also have on the right side of the portion of the diagram, we have H2. And h2 stands for the vertical distance between the point of tangency and the highest point of the summit or the lowest point of the sag curve. So this is basically the same as the two previous examples, and it only differs by a mere fact that h1 involves the point of curvature, whereas h2 involves the point of tangency. So that's basically what we need to remember for h1 and h2. They are the vertical distances. Moving on, now we have G1. As labeled in the diagram here on the lower left, we can see that encircled, it is the grade in percent of the back tangent, or basically the tangent that involves the point of curvature. Whereas we also have G2, which is basically the same as G1 and the previous examples, and it also differs by a mere fact that G2 also involves the point of tangency. So G2 is the grade in percent of the forward tangent, or the tangent that passes through the point of tangency. So that's basically it. So G1 and G2 are just like the previous examples, H1 and H2, and S1 and S2. They're basically just the opposite, as every variable labeled with 1 involves the point of tangency. I mean the point of curvature or the back tangent, and every variable ending with 2, which is G2, S2, and H2, involves the forward tangent or the point of tangency. So now we arrive at the last three elements of the vertical curve. So we talked about every single variable so far, and now we are coming to an end. So hopefully you have followed me all this time. So let's start off with the small letter A. So the small letter A represents the vertical distance between the point of curvature and the point of intersection. So basically, it's you just take the difference between the point of intersection and the point of curvature. You just take their vertical difference, and that is basically their distance. So B, on the right side of the diagram, as you can see, it is encircled there. It is basically the same as A, but B is the vertical distance between the point of tangency and the point of intersection. So again, you just take the vertical difference of their distances, and basically that's it. So lastly, we have H. So this is the vertical distance between PI and the curve. So to sum it all up, A will be the vertical distance between the point of curvature and the point of intersection. B is the vertical distance between the point of tangency and the point of intersection. And H is the vertical distance of the point of intersection and the curve. So all these three variables in the latter are basically the distances of the point of intersection to either of the points that are there. So basically either of the points that are points of tangencies in the vertical curve. That's basically it. So again, I hope these elements are useful, as now we are going to move on to the formulas and how to apply these concepts. So hopefully learning these elements will make us understand the formulas better and faster, since now we know what each element does and what each variable serves as their purpose.
With a symmetrical curve, given here are some formulas that can be used for a symmetrical parabolic curve. We will be deriving each formula here in the next few slides. For the first formula, we have A equals 1 half G1 times L and B equals 1 half G2 times L. So here we use the concept of slope equals rise over run in order to get the formula. As seen in the triangle below, we have G1 as the slope, A which is the vertical distance between PC and PI as the rise, and L over 2 as the run. So we have G1 equals A over L over 2, which then simplifies into A equals G1 times L over 2. In order to get B, we use the same concept as the previous slide, and we can get B equals G2 times L over 2. For our next formula, so we neglect the signs of G1 and G2 in order to get the formula S1 equals G1 times L all over G1 plus G2. So first, we have the equation of our parabola y equals kx squared. And obtaining the first derivative, we get dy over dx equals 2kx. And since we know that dy over dx is the slope of the tangent line, therefore we have dy over dx equals g1 and x equals negative s1. And it's negative because it is going to the left side of the reference point or the vertex. And dy over dx equals g2 and x equals L minus S1. So substituting these values, we get G1 equals 2k S1 and G2 equals 2k times L minus S1. So dividing the two given equations, or the equations we just found, we have G1 over G2 equals to 2k S1 all over 2k times L minus S1. So simplifying, we get G1 over G2 equals S1 over L minus S1. And simplifying further in order to isolate S1, we get S1 equals G1 times L all over G1 plus G2. For formula 3, we have H1 equals 1 half G1 S1 and H2 equals 1 half G2 S2. So this is using the vertical distance equals area under the gray diagram concept. So the area of a triangle is obtained by the formula area equals 1 half base times height. So we apply that here, where G1 is the height, S1 is the base, and H1 is the area of the triangle. So we get H1 equals 1 half times G1 S1. So apply this with the H2, G2, and S2, and we get H2 equals 1 half G2 times S2. For formula 4, we have H equals 1/8 L times G1, G2. So first we look at the figure. So we extend the line PCPI such that it will create a translation of the triangle in the bottom left, which is the PCPI, and then the center of the curve, I guess you can say. So we translate it to the upper right side. So since it is a translation, the two triangles are equal, the bottom left and the upper right. So now given in a previous formula, we have A equals G1 times L over 2 and B equals G2 times L over 2. And so applying similar triangles, we get 2H over L over 2 is equal to A plus B over L. And since we have the values of A and B, we can rewrite the equation into 2H over L over 2 is equal to L over 2 times G1 plus G2 all over L. And then we simplify these equations, and we simplify the equation, and we get H equals L over 8 times G1 plus G2. So for the next formula, we have x squared over y equals L over 2 squared over h. So we use the concept, the square property of a parabola. And in summary, it states that given 2 points in a parabola, we have x1 squared over y1 is equal to x2 squared over y2, where the x value is the x distance from the point to the vertex, while the y distance is the distance from the point to the vertex. So applying this, we get x squared over y is equal to L over 2 squared over h. So for our sample problem, we got this problem from our module in Canvas, so you can always just view it there if you want. So a grade of negative 4.2% grade intersects a grade of plus 3.0% at station 11 plus 488.00 of elevations 20.80 meters. These two center grade lines are to be connected by a 260-meter vertical parabolic curve. Question 1. At what station is the cross drainage pipes be situated? And question 2. If the overall outside dimensions of the reinforced concrete pipe to be installed is 95 cm and the top of the culvert is 30 centimeters below the subgrade, what will be the invert elevation at the center? So the first question is asking, at what station should the cross drainage pipes be situated? So this is basically asking where the lowest point of the curve is situated. So given from the grade diagram below, as in the figure below, we get S1 over 0.042 is equal to 260 over 0.042 plus 0.03. And 260 is the length of the curve, or L. So we get S1 is equal to 151 and 2/3 meters, or 151.67 meters. So we then get the D value, so the distance, which is the distance from the PI to capital A. So the capital A there you see, which is labeled as the lowest point of the parabola. So D is equal to S1 minus 130, as you can see in the graph. So S1 is equal to 151.67 minus 130 meters. So we have D is equal to 21.67 meters. So we then get the location of station A through getting the value of station PI plus D. So station PI has a value of 11,488 meters. So 11,488 meters plus 21.67, we get 11,509.67 meters. So station A is equal to 11 plus 509.67 kilometers. The second question is asking, what will the invert elevation be at the center? So it is basically asking what is the elevation of the point at the bottom of the pipe. So first we get the vertical distance between PC and PI, which is small letter a, not to be confused with point A, which is the lowest point. Then, so we have A equals G1 times L over 2. So A equals 0.042 times 130, and we get A equals 5.46. So that's the vertical distance between PC and PI. So next, we get the vertical distance between PC and the lowest point, the point A, not the small letter a, but big A. So we label this A1 as it is not the elevation of point A, but it's just the vertical distance between PC and point A. So A1 is equal to 1/2 S1 G1. So substituting the values, we have 1/2 times 151.67 times 0.042, and we get A1 is equal to 3.18 meters. So now we will look for the elevation of point A. So elevation of point A is equal to elevation of PI plus small letter a minus A1. So small letter a minus A1 is basically that small distance there from PI to the vertical distance from PI to point A. So next elevation, so we have elevation A is equal to 20.80 plus 5.46 minus 3.18 meters, which results to 23.08 meters. So then we get the elevation of the invert. We have the elevation of point A minus 0.30 meters, 0.30 meters minus 0.95 meters. And so we compute that and we get the elevation of the invert is 21.83 meters. And there you have it.
We now proceed to another type of curve named unsymmetrical curve. So the thing that makes an unsymmetrical curve different from a symmetrical curve is that the length from point PC to point PI is not equal to the length from point PT to point PI. Unlike from a symmetrical curve, both of these lengths are equal. As you can see in the figure below, we have lengths 1 and 2, which indicate that both measurements are not the same. For our first formula, we follow the same idea from that of a symmetrical curve. Previously, A was equal to G1 multiplied by L over 2, and the same is applied to B. But now, since we assume that both lengths are not equal, A is now equal to G1 multiplied by L sub 2 since we're using the right side of the parabola. And the same goes for B. So now C is equal to L sub 2 times the sum of G1 and G2, and by similar triangles, we have 2H over L sub 1 equal to L sub 2 times the sum of G1 and G2 over L. Finally, after simplifying this, we get H is equal to L sub 1 times L sub 2 times the sum of G1 and G2 over L. For our second formula, we still use the square property of parabolas, and we have the following equations presented below. So instead of having just one formula by using this property, we now have two because again, the lengths are not equal. Lastly, when we have h to be greater than g1 times L sub 1 over 2, s is equal to g1 times L sub 1 squared divided by 2h. So s here is the length of the horizontal line from point PC to the highest or lowest point of the parabola, while a value of h that is less than g1 times L sub 1 over 2, s is equal to g2 times L sub 2 squared divided by 2h. And what this means here is that S is the length of the horizontal line from point PT to the highest or lowest point of the parabola. So for a quick comparison, both symmetrical and unsymmetrical are similar to each other. But the only difference between the two is because of them having different horizontal lengths to their point of intersections. Therefore, a part of their formula are also tweaked because of this.
Problem number 1. A forward tangent of 6% was designed to intersect a back tangent of negative 2.5% at a proposed underpass so as to maintain a minimum clearance allowed under a bridge, which crosses perpendicular to the underpass. A 220-meter curve lies on the side of the back tangent, while a 100-meter curve lies on the side of the forward tangent. The stationing and elevation of the grade intersection is 5,535 and 100 meters respectively. The center line of the bridge falls at 5,585 and the elevation of the underside of the bridge is 105 15 meters. Determine the minimum clearance of the bridge if it has a width of 10 meters. Napakahaba ng problem. Okay. So, meron tayong forward tangent and back tangent. So, ang back tangent natin is negative 2.5%. So, pababa, descending. Okay. Ito siya. Okay. Then, yung ating forward tangent is paganyan. Okay. So, ito ay positive, what? 6%. Then, ito niyan is negative 2.5%. So, paano matukoy yung back tangent and forward tangent? So, from this point, titingin tayo mula sa likuran. So, ito yung back tangent. Ito naman, titingin tayo mula sa harapan. Ito yung forward tangent natin. Okay? Then, okay. Yan. Yan. So, ito yung ating curve. So, this is PVC. And this is PVT. Tapos, meron silang length. Okay? This is PVI. Binigay yung length niya from PVI to PVT and PVI to PVC. So, sabi dito, 220 meter curve lies on the side of the back tangent. So, this is 200 meters. And yung naman, so forward tangent is 150 meters. Ayan. So, binigay yung L1 and L2 natin. Tapos, maglalagay raw tayo ng, yes, meron pa tayong station sa PVI na. Ang station natin sa PVI is 5,535. Okay, so 5,535. Tapos, ang elevation niya is 100 meters. Ayan, dito sa point na to. Okay? Tapos, iti-design natin yung ating curve na merong overpass. Yun yung bridge natin. So, ngayon, yung bridge natin is nasa station na 5,585. So, lagpas ng PVI. So, sabi natin ito yung ating bridge. Yan. Okay. Ito yung ating bridge. Tapos, ang station niya sa center line, ito, is 5,585. Okay? Tapos, ang length natin, or yung width ng ating, bridge is 5 meters. Or ang total niya is 10 meters. Okay? Tapos, ang elevation daw nito, ito, ang eled ng ating, anong term na ginamit doon? Underside. So, sa baba nun, 115 meters. Yun yung elevation niya. Okay? So, ngayon, ang pinapahanap dyan is yung minimum clearance. Meron tayong dalawang clearance dito. Actually, tatlo eh. Itong, dito sa side na to. Okay? Then, dito sa gitna, sa center line. Then, dito. So, ano yung minimum clearance dyan? Ito yung minimum clearance. Kasi ito yung pinakamaliit na clearance. So, paano nyo po natukoy na pag ganito siya? Okay? Kasi papataas na to eh. Kasi sag curve tayo, tama ba? So, papataas na to. So, ibig sabihin, ang minimum clearance niya is dito. Imposible naman niya na biglang bumaba ng paganyan. Tama ba? So, ito yung minimum clearance natin. So, ito na lang hahanapin natin. Okay? So, ngayon, paano to? Okay. Ayan. So, ito, meron tayo na to eh. Tama ba? May elevation tayo dito. So, pwede natin kunin to. Hanggang dun sa minimum clearance natin. Ito. So, sabi natin letter A. Then, kunin natin tong point na to. Ito. Sabi natin Y1. So, kung may Y1 tayo, dapat meron tayong X1. And makukuha natin X1. Tama ba? Kasi meron tayong 150 dito eh. So, ito, meron tayong length nito. So, isa-isay natin. Yan. So, A muna tayo. Then, ito, ang distance na to is okay, may station tayo dito na 5,585 eh. Then ito, 5 meters. Additional 5 meters. Tama ba? So ito, 5,585. Ito naman, 5,535. So sa center line niya, 50. Okay, plus 5. So 55 meters. Then ito, G2. Okay, therefore, ang ating A is equals to 6% multiplied by 55 meters. So, ang A natin, okay, is equals to 3.3 meters. Ayan. Then, kuha natin yung y1. Kung meron tayong x1. Then, meron tayong x1, syempre makuha natin yan. Kasi meron tayong length dito na 150. Tama ba? Then, minus what? 55 meters. So, x1 is equals to 95 meters. Ayan. Makuha natin yung y1. So, ang y1 natin over x1 squared is equals to h over L. Yes, L1. Sorry, hindi na siya L1. Nasa L2 tayo L2 squared. So, kunan muna natin yung h. H is equals to L1 multiplied by L2 multiplied by G1 plus G2 over 2 multiplied by L1 plus L2. So, ang H natin is L1 na 220 multiplied by L2 na 150, G1 na 2.5% plus G2 na 6% over 2 multiplied by 220 plus 150. Kaya ang ating H is equals to 3.791 meters. Makuha natin yung Y1. So, Y1 is equals to X1 squared. So, 95 squared multiplied by H na 3.791 over L2 na 150 squared. Okay? So, ang ating Y1 is equals to 1.521 meters. So, makukuha natin yung minimum clearance natin. So, paano natin makukuha yung minimum clearance? So, minimum clearance is equals to ito. Pag-minus natin, tama ba? So, 115 minus 100 para makuha tong total length na to. Tama ba? Or total height. Then, saka natin i-minus yung A, saka natin i-minus yung Y1 para makuha yung clearance natin. So, minus A, which is equals to 3.3 minus Y1 na 1.521 meters. Kaya yung ating minimum clearance is equals to 10.179 meters. Ayan. So, karaniwan, lumalabas sa board exam, alam ko Kalimutan ko na. Okay, pero ito, nung nag-aaral ako, kahilig ng professor kung ibigay itong gantong problem. Tapos, di ko siya nasagot noon. Di ko siya nasagot. Pero ngayon, nasagot ko na. Kasi nalilito ko dati sa curve. Without realizing that, we only consider horizontal distances sa vertical curve lamang. Okay? So, yun lang i-consider natin. Puro horizontal and vertical distances. So, ito yung ating problem number 1 for the unsymmetrical curve. Okay?
So basically, that's all for the sample problem that involves the unsymmetrical curves. So he may have used like slightly different variables from what we are used to, but what is important is that we know the function of the element or variable. So basically, we can just understand that what his variables used are equivalent in our set of variables. So that's all for our report, and I hope that you learned a lot, and especially that this is a topic that is kind of like similar to the horizontal curve. So thank you for listening.